Let's talk about arc length. This is our formula from back in chapter 8. S equals the integral of a to b square root 1 plus f prime of x squared dx. Let's figure out the equivalent parametric form for this integral. So here we go. We're going to, of course, switch it to alpha to beta. Alpha, beta, square root 1 plus, that's all the same. Then our derivative, remember that's dy over dt over dx over dt, quantity squared. And dx, kind of like what we did in area, dx over dt times dt. Okay. Now it turns out we're going to work with what's inside that square root. Here's the next step. Think of 1 as dx over dt over dx over dt. Okay? Actually, we need to square it. Dx over dt squared over dx over dt squared. And then we're going to combine numerators. And I'm just going to go for it right there. So dx over dt squared over dx over dt squared is the 1. And then there's the other piece. Let me zoom in just a bit. It's a bit far away, I think, for what I've got here in the center of the page. All right. So next, what's going to happen? I'm going to take what's underneath here, and I can pull it outside of that square root, right? When I do, the square root and the square cancel, and it's in the denominator. So when I pull that dx over dt out, it cancels with this dx over dt. And I get something that's actually really nice. Integral alpha to beta, square root. All that's left here is the numerator, dx over dt squared plus dy over dt squared dt. Some might argue this is a better form for arc length than this was. Simpler. Derivative of x squared plus derivative of y squared, all square rooted. Almost gives a feel for like a Pythagorean theorem there. I guess, that has its roots in the Pythagorean theorem as well. Okay, just one example here to finish off this section. Let's find the arc length from, trying to get that all on the screen. The arc length from t equals 0 to t equals 2. X equals t squared. Y equals 2t. We're going to keep it simple. Again, I would recommend start off by graphing. So here's the graph. I've got the derivatives there also, but the graph ends up being this sideways parabola. But if we look at it from t equals 0 to t equals 2, t equals 0, well, we can tell that's going to be 0, 0. T equals 2 is at 4, 4. 4, 4. So it's just this portion that I've tried to bold like that. Okay. So then our derivatives, dx over dt equals 2t. dy over dt equals 2. And all right, we're going to plug those in to our formula. Again, it's just square dx over dt, square dy over dt under a square root. And of course, our values of t is 0 to 2 in the integral. Pretty nifty. Okay, well, let's try it out. If we square both of those, right, we got 4t squared plus 4 underneath. What might we do at this point? Let's factor out a 4, even move it out front completely. So 2 integral 0 to 2 square root t squared plus 1. Okay, and now at this point, you know, it's just a matter of can we perform that integral. And square root t squared plus 1, you know, if we were in class, I'd say, hey, what integration technique should we use on that? And, well, if some of you guys out there can think back to chapter 7, that would be a trig sub. We would set it up, draw the triangle, go through it. Turns out in the midst of doing that trig sub, once we simplified everything, you would need integration by parts, and it would actually be a fairly challenging one. Another technique, if it was allowed, would be to use a table of integrals. I'm just going to go ahead and tell you the final answer. To not go through all the trig sub steps, because it is quite a challenging one. If you come across something like that in homework, of course, that is up to you to get through. If you want to confirm your answer with a table of integrals, that would be pretty quick. This would match up pretty nicely. Turns out it's 2 square root 5 plus the natural log of 2 plus square root 5, or if you want the decimal, 5.916. Okay, that is it for 10.2. I'll see you in the live session.